it's 8 a.m. Pacific time. Let's get started. Good morning, good afternoon, good evening. Welcome to today's tinyML web talk session. I'm Wei Xiao from ARM. I will be your moderator today. So first, a very special thank you to our sponsors, DeepLight, Kixo, Edge Impulse, Reality AI, Maxim Integrated, and SynSense. I'm proud to announce that ARM also became tinyML's strategic partner. On October 27th, we will have Christopher Ardis from Maxim Integrated to talk about reduce energy consumption while increasing complexity of AI at the edge application. And Sekashenha Desduba from Edge Cortex to introduce using AI to design energy-efficient AI accelerators for the edge. The talks are also scheduled at 8 a.m. Pacific time. If you're interested in presenting, please send your proposals to talks@tinyml.org. We're also excited to announce that tinyML Asia will take place virtually between November 16th to 19th this year. The full program agenda can be found at www.tinyml.org/Asia2020. In the meantime, we're seeking video posters submissions. Abstracts are due by October 31st. Additional sponsorship are also available. Please contact Betty at tinyml.org for more information. The speaker today is Rajen Bhatt from Qeexo. So his talk is Qeexo's runtime-free architecture for efficient deployment of neural networks on embedded targets. Rajen is the director of engineering at Kixo, leading a team of machine learning engineers to develop revolutionary machine learning platforms and products. His area of expertise includes machine learning, computer intelligence, computer vision, and product engineering. He has authored more than 35 peer-reviewed papers, a book on pattern classification algorithms, and is the inventor and co-inventor of 20 granted patents in India, US, and South Korea. Welcome, Rajen.
Thank you, Wei. Greetings, everyone. Thank you for joining the talk. Before we go into the framework discussion, I'll present some key facts about Kixo. Kixo has been engaged in the development of tinyML applications since its inception in 2012. In 2017, Kixo has become one of the world's first companies to develop and deploy convolutional neural network-based tinyML models on the smart devices. And since our inception, and since we have invented this particular framework of deployment of deep learning models, Kixo's AI models are running on more than 400 million smart devices worldwide, and they are increasing as we speak. So in the heart of all this development is the framework which we have invented for the runtime-free model conversion and deploying them onto the tinyML hardware platforms. If you want to try Kixo AutoML, you can go to the https://kixo.com. That's our website, and you can register for the AutoML product for free. In this discussion, we will focus on two key aspects of Kixo's architecture. The first one is extremely small overhead. I will explain as we progress in the discussion that what we mean by overhead. We will see that compared to any other frameworks for model conversion and deployment, this particular framework builds lighter binaries with no impact on performance and latency. The second aspect is it is extremely easy to use. we will see that the framework abstracts all the complexities which are related with the model conversion and deployment from end users and making it extremely easy to use with absolutely no coding required at the user's end. In order to do that, we will take one tinyML hardware platform, and here I am considering Arduino Nano 33 BLE Sense. This particular hardware platform is having 9-axis IMU, varieties of environmental sensors, microphone, proximity, light sensors. This platform is running on 32-bit ARM Cortex M4 CPU operating at 64 megahertz. So it allows us to do 32-bit floating point operations on the device. And it has an IDE support, which can convert TensorFlow built neural network models to Arduino sketches, and then we can deploy those sketches on the Arduino platform so that it becomes an AI node. What is a general interest of deploying tinyML models, neural network-based tinyML models in particular, is that we want to use either TensorFlow or PyTorch and build these 4 widely known or widely used neural network models: convolutional neural networks, feed-forward, densely connected artificial neural networks, RNN, that is a recurrent nature of the neural networks, and CRNN, and then deploy them on the tinyML platform so that we can run them from a platform which has several sensors and a microcontroller. In order to do that, we will be taking 3 benchmarking candidates. We will be taking 3 frameworks which are available. The first one is the TensorFlow Lite Micro, and we will be using TensorFlow Lite Micro through Arduino IDE because it allows us to basically ingest the TensorFlow Lite developed model and then convert them to the Arduino sketch and then deploy them onto the Arduino hardware. The second framework we will use is MuTensor, which is basically a machine learning inference framework for neural network kind of models, which is built on TensorFlow Lite, and it is optimized for ARM processors. And it can also convert and deploy NN models. And the third one is Qeexo AutoML, which is fully automated machine learning platform for sensor data. And it can build models, convert them, and then deploy them for the tinyML targets. In addition to that, it can also do several other things, for example, configuration of the sensors, collecting the data, labeling the data, managing the data, and also doing the live performance analysis and the calibration. What we will do is we will develop 2 example classification libraries. We will take first example as a fruit classification, where we are going to use the Arduino color sensor, proximity and ambient light sensors. And then we will try to recognize whether the fruit is apple, banana, or orange. So it's a 3-class traditional classification problem. And the second problem we will consider here is the musical instrument air gesture classification problem. I have inserted a YouTube video link over here, and you can see our CEO Sang doing 2 different kinds of gesture. One is the drum gesture and the other one is the violin gesture. And the Arduino platform is attached to this particular stick so that we can actually record the accelerometer and the gyroscope data. And based on those acceleration and gyroscope data collection, we can try to recognize whether someone is either playing a drum or either playing violin. Now, we have observed that there are these 2 classification problems. One problem is relatively easy, which is fruit classification. And because it is a relatively easy problem, it results into a smaller model architecture. And the other one, music instrument air gesture classification, It's a relatively complicated problem. It has a complex decision boundaries. It's a nonlinear classification problem, and that is why it results into large model architectures. And we have also selected these two applications to demonstrate the behavior with the high ODR sensors and the low ODR sensor. We can see Excel and Gyro here are operating at 476 ODR, 4G and 250 DPS, and proximity and ambient lights are operating at 100 Hertz ODR. This is the results we can see here. And so here we can see the models which are being converted using these three different frameworks, TF Lite, Micro, MuTensor, and the AutoML framework. And we see the size of the models which are being deployed. Now I want to first explain what is the empty binary size. So empty binary size is it's just the framework or device driver code. Empty binary does not have any model at all in it. And the size of the empty binary can slightly vary depending on the sensor configuration, that what sensors we are choosing, at what rate we are pulling the sensor data. And it's basically an embedded piece of code which is needed in order to just simply operate the hardware. So that is an empty binary size. And within the empty binary, when we put the model weights and then we put the interpreter, it means that how to interpret the model, how to do the forward pass of the model. If we add all these together, then what we get is a total binary size. So we can see, for example, here that in the AutoML, the 74 kilobyte is the empty binary size. And when we are adding the model weights and the overhead size, which is an interpreter size, then it becomes the 78 kilobyte. Now we can see here that for the fruit classification problem, as I have explained earlier, that it is more or less linearly classifiable problem. We are getting models which is very small, which is the parameters are just 1.4 kilobyte. And for the musical instruments classification problem, we are getting the model which is bigger, way bigger than this particular model, with parameters, model weight size, almost 156 kilobyte. When we compare these three frameworks, we see that the model weights are approximately the same. It's ranging from 1.4 to 1.7 kilobyte for these three different architectures, 155 to 157 kilobytes for the other classification problem. So model weights are just the layer weights, basically. It does not have any inference. It's purely the model parameters. And then what we have is an overhead size. So in the neural network models, once we have the parameters, we need to infer that model. We need to run the forward parts of the model. And for that, we need an interpretation logic written for these parameters. So we can see here that the interpretation logic is just 2.6 kilobyte for AutoML versus almost 79 kilobytes for TensorFlow Lite Micro. And we can see that remains about 2.05 kilobyte for AutoML in the second problem. And it goes to up to 88 kilobyte for TensorFlow Lite model. So we can see here in this experiment that whether the problem is complex or the problem is simple, the overhead size for the Kixo AutoML doesn't change drastically. And also the overhead size is magnitude of order smaller than TensorFlow Lite Micro or MuTensor. And ultimately that results into lighter binaries, which can easily be deployed onto these particular targets, which is here Arduino Nano 33BLE Sense, or even if we have targets which are more memory conservative, then also we can easily deploy these models. Second thing is that the classification performance does not change because we are using exactly the same model. So the classification is the same. There is no change in the classification performance, and there is no change in the latency. And that's why they are not being captured here, because it remains the same. What we are comparing is just the size of the model at the same latency and at the same performance level. So here is the workflow. If we want to operate these three different frameworks, and I'm keeping the data collection and training of models outside the workflow, because these two steps are the key essential steps which we need in order to build any machine learning model. So I'm keeping them outside of the workflow. Now, if we want to use the TensorFlow Lite within Arduino, then once we develop the TensorFlow Lite model, then we basically convert to C++, and then we create an Arduino sketch file, and then we basically deploy the Arduino sketch file, which is equivalent to flashing the model.h and the main into device. And once that has been uploaded, then we can do the classification. And internally, it uses the TensorFlow Lite Micro interpreter for doing the classification. When we try to use mu-tensor, we need to convert it to the protocol buffer and then convert it to the mu-tensor C++ code. And then again, we create an Arduino sketch, and then we do the flashing. And then once it is flashed, it performs the classification. Now, these two workflows still need significant amount of coding in order to achieve this. When we want to do the same thing using Qeexo's AutoML platform, we convert these models to C using NN to C utility, and then flash to device using AutoML, and then the flashed binary does the classification using predict.c file, and then tenseval.h inference engine. I'll be explaining what is predict.c file and tenseval.h inference engine is, but in this particular framework, these are just the steps of the framework. Absolutely no code is required in order to flash these models on the target. So this is the Kixo AutoML workflow for converting the neural network based models and then deploying them on the target. What we do is, once we have collected the data, prior to that we configure the sensors, collect the data, label the data, and then once we have all the data collection in place, then we use either TensorFlow Lite, or PyTorch to build these models. We use TensorFlow to build CNN and ANN models, and we use PyTorch to build RNN or CRNN models. Once we have these models, the TensorFlow models are being represented in HDF5 format, and the PyTorch models are being represented in ONNX format. And then there is an NN to C conversion API developed by Kixo. This particular API ingests these two model formats, so we can ingest either HDF5 or the ONNX format. And after ingesting these two models, it basically generates the predict.c file and the tenseval.h file. And once we have these two files, predict.h and tenseval.h, then we can compile them into binary file or into the static library. And then we can simply flash them onto the embedded target. Now, what is predict.c? It is a C source file. It basically interprets the graph. It basically interprets the forward pass of these 4 different kinds of neural network. And it contains also the model parameters in static constant arrays. Tenseval.h as its name is very intuitive, it is our own internally developed tensor evaluation library. So it basically a collection of highly optimized C code, which does all kinds of mathematical operations which are needed in order to do the forward pass of the model. And then we generate two files. One is the binary file, which can straight flash to the device. And then once it is flashed on the devices can directly be deployed on the field, or we can do the live testing. Because these binary files have all the sensor configuration built in, ODR, FSR of the sensors. It basically monitors the sensor data thread. It collects the sensor data, then it does the chunking, and then it performs the forward pass of the network models. We also generate the .a file, which is a static library. So if I want to integrate this machine learning model into my own program logic, say I'm building a smart countertop or I'm building a smart wall, right? Then I'm not just interested in getting 1 or 0 classification output. I also want to do something else on top of that classification output, where I want to grab the classification output and I want to integrate that classification output into my own logic to do something else, either to send push messages or to generate the alerts or to do something else. So in that case, we also provide the .a file, which users can link against their own programs. So NN2C does basically everything. In fact, NN2C, it's a Python code which dynamically on the fly writes a C code. So there is a code which writes a code. It's a robot. So this NN2C Python interface generates these two files dynamically, predict.c and tensorflow.h, by ingesting the HDF5 file format or by ingesting the ONNX file format. And both of them can be generated using TensorFlow or PyTorch. And data collection is integrated in Qeexo AutoML. So, it does all these things. Plus, in addition to that, you can actually build a data collection library and flash it onto the device so that you can do the data collection and labeling. Briefly, NN2C.py utility does the following operations. It loads these two kinds of models and then walks through these models layer by layer. So it basically walks through the computation graph layer by layer, then sorts the graph, and if there is any kind of quantization is done or any kind of quantization aware training is performed, then it also performs the quantization. And this diagram shows that what kind of information is there in the model. It basically has the information like what are my inputs, what are my outputs, I'm doing what kind of convolution, what is my kernel, what is my bias, what kind of activation function I'm using, for example, leaky ReLU or dropout, whether or not I'm doing zero padding. It basically reads through all this information and generates the C code on the fly dynamically. And it's also easy to support for additional layers, or if you want to write any additional tensor operation, because we simply just append the tensorflow.h file. And this is the brief comparison of the workflow and the user experience. And we can see here that Kixo AutoML has the sensor configuration and these two different kinds of continuous and event data collection. And from building and training the model to flashing, everything is automated and abstracted. While you need coding, you need some research in order to figure out what are exactly the steps for actually building and then flashing the models. And in addition to that, the models which are being generated by Kixo AutoML, they are magnitude of order smaller. So it gives an opportunity to either make bigger models because they are going to fit into the given flash and RAM size, or if I have a device which is more memory constraints, I can still use Kixo AutoML to deploy the CNN models or NN, RNN, CRNN models on these devices. This is the list of some of the supported layers. We can see here that most of the commonly used layers are supported. Most of the commonly used operators are also supported. We can see here there is a support for the GRU and LSTM layers for developing RNN and CRNN models. Several kinds of activation functions, ReLU, leaky ReLU, softmax, sigmoid, quantization for dense layer, 1D, 2D, zero padding, convolutions. Most of the commonly used operators are supported in the framework. So I conclude my talk here. I have a few takeaway points for the conclusion. The first one is, as I have already cited earlier, that when we build and deploy neural network based models using Qeexo AutoML, we build models which are extremely light in size compared to any other non-frameworks, and they have extremely small overhead compared to any other tinyML frameworks. It's an end-to-end sensor data platform. The example which we have considered here was M4F ARM Cortex architecture, which can do 32-bit floating point operations. It can support targets up to M0. So the other reference platform we have also is Arduino Nano 33 IoT, which is an M0 device, which does 32-bit fixed point operations, and it has 6-axis IMU sensors. And our discussion today mostly focused on the neural network-based models. In addition to neural network-based models, AutoML can also build extremely lightweight and low latency machine learning models using several other different kind of machine learning algorithms, like logistic regression, GBM, random forest, and it can also do the anomaly detection models using isolation forest, one class HVM, Aron, one class random forest, and such. So as thank you, Wai. Thank you, everyone.
Thank you, Rajen. So let's address some of the questions from our audience. So we have a question regarding your comparison slide. Why the model weights are slightly different between TensorFlow Lite and AutoML. Can you elaborate on why TensorFlow Lite overhead is so significant?
So the TensorFlow Lite overhead is so significant because there is an interpreter. The whole interpreter needs to be built inside the library. And TensorFlow Lite interpreter itself is about 100 kilobyte. And there is another interpreter, which is TensorFlow Lite Micro interpreter, which is of about 25 kilobyte. So because it needs the whole interpreter to be baked inside the binary files, that's why the overhead is significantly higher compared to the Qeexo AutoML. What Qeexo AutoML does is that it only puts those many operators and only puts those many layers of C code into the final binary, which are actually needed and which are actually encountered during the forward pass of the models. So because, as I said, the Qeexo AutoML framework is actually a code that writes a code. So it would basically look at the model and then would generate the C code dynamically on the fly. So it would only generate the C code, which is only required as much as needed to compute the forward pass operations.
Thank you. Another question from the audience. Your overhead size looks great. However, does this also hold true when deploying really deep networks with hundreds of layers, for example, deep ResNet?
Right. Yes. As I said, the overhead is not going to blow significantly, because what would happen that if it is using the same kind of layers again and again to do the operation, then it would basically write those layer information only once into the C code and it would not repeat it. So overhead size is not going to, overhead size is going to increase when we are going to have a very, very deep models. But the point here is that the overhead size is not going to grow exponentially, or at least it is also not going to grow linearly proportional to the size of the model. So if I'm having a model which is a 5 megabyte in size, for example, I may encounter an overhead of 50 kilobyte, but it is still significantly smaller compared to the model parameter size itself.
Okay, we only have time for one last question from the audience. Is Kixo open source? Is it available for developers or contributors?
No, it is not open source yet, but you can go to the Qeexo.com website and then experience the full platform. And contact us if you have any kind of open source ideas or want to collaborate with Kixo for the open source framework. And just there are frameworks and there are contact us kind of channels established. So just write to us and we will get back to you.
Thank you, Rajen. So huge thanks again to our tinyML talk sponsors: DeepLight, Kixo, Edge Impulse, Reality AI, Maxim Integrated, and SynSense. DeepLight provides an AI-driven optimizer to make deep neural network faster, smaller, and energy efficient. Edge Impulse offers online tinyML lifecycle solution, which transform developers' abilities to deploy machine learning for embedded devices. Maxim Integrated enables edge intelligence with their sensors and signal conditioning technologies. Advanced AI acceleration solutions is coming soon. Kixo AutoML platform builds tinyML solutions for the edge using sensor data. Reality AI offers optimized feature discovery, compact embedded code, optimized toolkit, and tools for managing the cost of data collection. SynSense builds ultra-low power sensing and inference hardware for embedded, mobile, and edge devices. ARM is also pleased to become tinyML strategic partner. ARM designs Cortex-M microcontrollers and Ethos U micro MPUs for tinyML applications. Early this year, we announced M55 and U55, which will enable AI everywhere on billions of power-efficient devices with greater on-device machine learning processing capabilities. So 2 weeks from now, on Tuesday, October 27th, 8 a.m. Pacific time, we will have presenters from Maximum Integrated and Edge Cortex to talk about their technologies. If you're interested in participating, please contact talks@tinyml.org. We're also extremely happy to announce that tinyML Asia Technical Forum will take place between November 16th to 19th this year virtually. Call for video posters is now open. Please submit your abstracts by October 31st. If you want to expand your business footprint in Asia, tinyML Asia will be a great event to sponsor. Please contact Betty for more information. Thank you for your presentation today, Dr. Rajen and Chandra. And we'll hope we can see our audience soon.